we'll start by अच्छा देखो कितने लोग बायोलॉजी देख के आए हैं एस्ट्रोनॉमी एक बार हाथ लगा लो अरे भाई भी नहीं ऐसा नहीं
तुम बता
हाँ तो मैं थोड़ा सा तुम लोग को एक शॉर्ट ट्रीटमेंट देता हूँ मैं बायोलॉजी की कुछ बात नहीं करता about 75 to 80% of the field studies exoplanets and habitability. उनमें से some of them have the motivation to find life, some don't. Most of them have the motivation to study planet formation and conditions for habitability. जब मैं conditions for habitability बोल रहा हूँ कि उनको लगेगा लोग या aliens ढूंढ रहे हैं नहीं ढूंढ रहे हैं जब हम एलियन की बात करते हैं we talk about search for life mission we mean microscopic और ये microorganism life forms in some water world not necessarily H2O so you get it just ठीक है तो about 75-80 studies this planet formation जिसमें they study the protoplanetary disk उसके बाद planet formation कैसे हुआ है बचा हुआ जो portion है astrobiology that deals with the थोड़ा बहुत biology that is called life in extreme environments मुझे इसके बारे में पता नहीं है so I will talk about that I will talk about that okay तो उसके बाद जो एक main question मैं पूरी talk के end तक हम डील करेंगे वो है कि is oxygen a confirming biosignature now biosignature anyone gets it what okay what do you mean by biosignature any rough idea
Things or signs in the atmosphere of a planet which indicate that life form will be present on its planet.
Yeah, it's just signs that life could be present in not necessarily in atmosphere also. Because there is something called technosignatures which studies such like remnants of a satellite around a planet, but that is a very far-fetched idea. Mangaram kahani hai. So, okay, the story starts from 1967 by Jocelyn Bell. She was a radio astronomer. While tuning her radio telescope and working on it, she discovered and noise signal which everyone thought was noise. But later they found out that it was a radio pulsar. You know what pulsar is? It's a pulsating, rotating neutron star. Okay, after that people started studying neutron stars and pulsars. Around 1992, in this system, you can see that here, this pulsar, around a pulsar, they found the first exoplanet. What happened? Pulsar rotates periodically. ठीक है? Periodic signal आ रहा है. समझ रहे हैं? Periodic signal आ रहा है. अच्छा उस periodic signal में there would be मानो एक हल्का सा noise है. Now that noise is also periodic. मतलब ऐसे बोल रहे हैं there is a little notch है it's going like this suppose हल्का सा notch है मतलब there is something which is orbiting the pulsar which is blocking the signal जब हम अपने field of view में देख रहे हैं anyone gets this much you're finding it movement okay so they found that the neutron star fluid system was hosting two exoplanets Poltergeist and Philothor. And after some time in 1994, they found that it also had Dragon, another moon-sized, size of our moon, an exoplanet size of our moon. So there the field started, they first discovered. People had speculations about exoplanets being present because of astrometry. Astrometry is because they study the wobble in stars. So if there is a star, there is a star, there is a planet. This planet is rotating 50 degrees. So this star would also rotate around its barycenter. It would be small considerably, but it would wobble. So people would thought कि ये wobble, if we found this wobble, we can say that it has a rotating planet around it. But the telescopes were not good enough to find this. Currently also astrometry technique is a very accurate technique to find, but we don't because even James Webb is not very good to find mass to astrometry very accurate. So, again, okay, this is don't get this, don't worry. It was basically the pulsar signal that they got, जिसमें इनको वो दिखा, ठीक है. उसके बाद around 1995, Michael Webb discovered the first exoplanet orbiting a sun-like star. Okay, you understand what sun-like star means, no? Mass of one solar mass. So, इसमें क्या difference था? Sun-like star means there are other solar planetary systems which are similar to our planetary systems and we can study them. Okay, they got the Nobel Prize in 2019 for it when they were giving Nobel Prize for things in physics. Yeah. Okay, अच्छा आगे चलो. यार वो चलो we will leave it. So आपको एक question ये आया, fine, they found a planet. Now I'm going to discuss something about how do we find a planet. Planet hunting कहते हैं. How do we find one? Any idea? Rough idea? Okay, please. So, you see, the number of exoplanets kept on increasing by the years, and till date we have very बहुत करना लिखा है. But my point is, till date we have more than 5,000 exoplanets known. So to study any exoplanet, we need some data to work on, कुछ observable चीजें चाहिए. So we'll first study how to find a planet. Okay, there are many ways to find a planet. I am going to tell you the one which are most basic. There are few parameters that I know and that I need to study a planet. Any guesses वो क्या हो सकते हैं? If I want to study a planet, what are the few parameters that I would need? Orbital distance, evolution. You need to study evolution. You need parameters, as in very fundamental parameters.
Formation and
Fine, but
distance from the star.
Very fundamental. It's mass.
Chemical composition.
No, chemical composition is fine. But firstly, you need its mass now. Think what this are. This is an introduction to try and keep things to the basics. So first thing you need its mass, right? Then what's the other thing you need? You need how big the planet is. You need its radius. So let's focus on the first these two quantities. To study a planet, I need its mass, its radius, and if possible, mostly I would get its distance from its host star. Okay. There are multiple methods. Radial velocity. This is the method that has been used to discover most of the planets. Then transit photometry, microlensing, and direct imaging. Okay. We'll go to each method. Okay. Radial velocity. So if you can see the red one. So the red dot is your star and the blue one is your planet. So ये अब जब घूम रहा है, suppose your observer is some right here. Okay. The star is rotating about its very center. Okay. Now जब star rotate कर रहा है, star is थोड़ा सा wobble आ रहा है because of the motion of the planet around it. So क्या होगा? The light that is coming from the star, you put it to a spectroscope, you get a spectrum. Right? You get the image? Now that spectrum would have a shift. When the planet is going like towards you, it would have a right shift. When it's going away, it would have a blue shift. You look at me. So with this, okay, now this is because of gravitation. So you think what quantity would I be able to get from this method?
Velocity of the star.
Velocity is fine, but mostly you will observe velocity. You just see the spectrum shifting.
The element by which the star is
Okay, that is you will get from the spectrum itself. But what I'm talking about is the spectrum is changing now. When the star is moving back, it would have a blue shift. When it's coming back, it's coming forward, it would have a red shift. क्या change है?
Smaller circles, radius, distance.
Mass of the
Yeah, you get mass. So basically, they are interacting gravitationally, na? So the only force of attraction currently is gravitation. So this shift in spectrum has happened because of gravitation. The quantity that you would get, calculate, would be the mass of the star. Now I can tell you the mathematics, but I'm planning to skip because बहुत सारा. Okay. So you got that much? First one, whether it was. Now the second thing comes. This is a good thing. It's called transit. Okay. Now there is something that I need you to understand. There are two terms that I'm going to use. It's called face on and edge on. Okay. When I say the planet I am observing is edge on, it means that this is my star and the planet is rotating like this. So if I observe from a telescope or something, I should see movement like this. Okay? It's edge on. What does face on means? This is my star and the planet is rotating like this. So when the system is face on, I cannot get a transit spectrum. Okay? For transit to happen, the planet has to cross the star. Okay, so it should happen in edge on. If there is a tilt, that can also happen. If the planet is far away, okay, something like 1 Earth mass or 1 EU. So if there is a tilt, if one star है, your star, if the planet is big enough, it will go like this, which is out. So you won't observe a transit. Light curve में डिप्लीट करेगा. अच्छा, transit होता क्या है? Basically, if you see, when the planet comes in front of the star, it's called a primary eclipse. Okay? There is a dip in the intensity of the light. Okay? This is called your primary eclipse. Okay? Now, okay, what do you think is happening when suppose the planet is tidally locked? Okay, you understand what tidally locked means, right? Like the moon is tightly locked with Earth. So when it is rotating, it's not shifting sides. Which means there is one side of the planet that is always towards the sun. Okay. Now, when the light from the star is coming, it will pass through the atmosphere of the planet. Right? The planet will have some atmosphere. It will pass through the atmosphere. Now what will happen? The molecules and the gases in the atmosphere would absorb some energy, and you know what spectroscopy is, no? Some rough idea about spectroscopy. Okay. So when you observe that way during a primary eclipse, so you would observe something called an emission spectrum. Okay. You get an emission spectrum. Now, so what is the quantity that you think you can get from transit?
Radius of the planet.
Yes, you will get the radius of the planet. And if the planet is, when we say radius of the planet, have you ever thought, does the radius has to be in the atmosphere or from the surface?
From the atmosphere.
From the center of the planet to the atmosphere. Okay. Now, usually in rocky planets, smaller planets, what happens? The atmosphere is very small. So the distance you get, we assume it to be roughly equal to the now the star will go, the planet will go back, and somewhere around here, suppose it's going like this, somewhere around here, when it's about to do a secondary eclipse. Okay, what is the secondary eclipse? जब वो सामने से आएगा, you would see there's a star, planet in front of it. This is your primary eclipse. You get an emission spectrum. The light बहुत ज़्यादा ऐसे क्यों? Okay. So when the planet goes in front of the star, so when it goes in front of the star, the light from the star would go through the atmosphere. The gases in the atmosphere would absorb some energy, go in a higher state, and you would observe an emission spectrum. You will get something. Now, the planet revolves and it goes behind the star. Now you can only see the star. This is called secondary eclipse. Okay? अब हमको बस star दिख रहा है, planet star के पीछे. So the light you are getting, the spectrum you are getting, this is the spectrum of the sun. the star, host star. Okay, just before the secondary eclipse happens, this is your star, this is your planet, just before. The spectrum you are getting is a mixture of the spectrum of the star and the the emission spectrum of the planet. Okay, emission spectrum समझ रहे हो? Light जा रही है, तो the molecules in the atmosphere absorb the light, went to a higher state. Okay. Now they would come back to their ground state. They would release some energy that would be in form of light. वो light हमारे पास आएगी, that would be our emission spectrum. अब during its revolution, you get both of the lights, the spectrum of the star and the emission spectrum. They would be overlapped. You cannot differentiate. Okay, it's a very small system, very far away. The moment the secondary eclipse happens, you are only getting the star's light. Now you subtract this. Subtract is a rough word, but to get an overall idea, you subtract the spectrum from the given spectrum, you will get the emission spectrum of the atmosphere. By studying these two spectrums, you can get the atmospheric composition. You can get the atmospheric spectrum. Now, we have got two quantities. हमको क्या मिल गया? We got the mass from the radial velocity method. We got the radius to the transit method and the spectrum. Okay. Now there is something called a retrieval. I will give you a very rough idea what retrieval is. Suppose you have a spectrum. Okay. So chemists in laboratories have studied some gas, if light is passed through, what is their spectrum? Multiple gas, they have a data set. Now, in a very rough way, you take a few gases, you put up a mixing coefficient, you mix them up in a simulation, you change their composition, and you get a spectrum. Now you try to match this spectrum that you have made with the spectrum observed that you got from the planet. It might match, it might not. If it doesn't match, you change your composition, your gases, until you get the exact spectrum, and with this, you will get the atmosphere of the planet. अभी मेरे पास तीन cases आ गए. I got the mass, I got the radius, I got the atmosphere. ठीक. इसके बाद the second image, this is from a method called direct imaging. Okay. From the terminology, you might get what direct imaging is. It's basically we are clicking a photograph of a star system. The planet is a little far away, so we get the. Now the black space that you see in between, you can see that now. There's a golden star in the space. There's an instrument called coronagraph that is installed in the telescope. The purpose of a coronagraph is to just block the star's light. Okay, it will block the star's light like this. Suppose there's a, it's like keeping a thumb. So you will get the flux image of the planet. Okay, this is the method used. We would keep another session on how to analyze this and all. That would be free. Now, I would go to something called a nebula like this. Okay. How a planetary system forms. First, you have a gas cloud. The gas cloud is rotating because it's rotating, it has a certain angular momentum. Okay. It has a certain angular momentum. It has a certain temperature. Now, what will happen? You'll have a solar nebula. The nebula rotate करेगा and it would form a disk. अच्छा, why would it form a disk? My favorite question. Yes. Any ideas? Why would a rotating dust cloud stabilize to form a disk? I mean, it's a very observed phenomenon. The moons of Saturn, the rings of Saturn. Why are they in a disk form? Sphere क्यों नहीं है उसके आसपास? Galaxies.
Same reason why Earth is also flat as it goes. Angular momentum conservation.
हाँ, angular momentum. थोड़ा सा, ठीक है. You can also see it with angular momentum conservation and something called you will see collisions. Suppose you have the dust cloud in a spherical envelope. Okay, they are rotating. Due to angular momentum, they come closer. अच्छा, now suppose sphere में कोई particle है, वो हर जगह move करने के लिए free है. So So they will collide. When these particles collide, they lose energy, and because of the angular momentum, while losing energy, they would eventually have a stable disk shape. The question है कि if the disk shape is stable and we get a disk shape because of this, why does dark matter around the galaxy is in a sphere? वो क्यों नहीं बनता disk? Anyone?
Because it doesn't interact with itself like collision. It interacts
It
with
does not
gravity.
dissipate energy. मतलब मानते हैं कि नहीं है, बंद करता नहीं ऐसा. ठीक है. Now accretion is बन गया. अब क्या होगा कि if you can understand because of this accretion ये घूम रहा है, so particles within would be interacting with each other gravitationally. तो वो आपस में आके form lumps. धीरे-धीरे these lumps would grow bigger, and because of increased pressure and temperature, you will get a protostar. Okay. Now this is called a protoplanetary disk. Okay, you have a protostar in between. You have a revolving disk of Astronomy. अब क्या हो रहा है कि you understand why the star is formed, ना? Gravitational force.
Accretion disk protostar के बाद में बनना चाहिए
नहीं
क्योंकि जब तक तुम्हारे पास बीच में कोई अच्छा सा
हाँ नहीं स्टार कंप्लीट स्टार नहीं बना है ना. It is a heavy mass core.
हाँ
So I cannot call it a star.
basically the protostar see तुम्हारे पास gas और dust है.
Yeah, so basically जब gas और dust rotate कर रहा है, so
gas और dust rotate कैसे करेगा?
it has accretion angular momentum. We assume that.
See then that means कि वो वहाँ का already कोई system था.
Yeah, you will get because of gravitation, you will get lumps. थोड़े-थोड़े core heavy mass core बनेगा बीच में.
हाँ.
That heavy mass core, so this is happening simultaneously. ये जो disk shape बन रहा है,
Okay.
and the star evolution. This is not separately. पहले disk बना फिर star बना. This is happening simultaneously. पहले एक छोटा mass बन रहा होगा, मैंने बोला accretion हो रहा है. वो धीरे-धीरे बड़ा हो रहा है. तब movement वो धीरे जब disk shape में आएगा, तब तक it would form a complete star cup.
Okay. So the disk shape should be along the equator of the
हाँ equator of the star. Okay. Now protostar बन गया. अब क्या होता है solar winds और जो gravitation की वजह से the elements, जो lighter elements हैं, they would be pushed back. Heavy elements तो ऐसे हैं. अब ठीक है वो जो आगे मैं ये बता दूँ कि okay. अब जैसे because you see उसमें accretion हुआ, grains जो थे particle के they came together to form a lump of mass that eventually transformed into a protostar. ये center में हुआ. But this may around multiple places. There would be more accretion similar happening. Like lumps of mass would come together. They would form something called protoplanets. Achha, one part of the field of exoplanets studies this planet formation from grain accretion. ये जो grain आगे लग रहा है, all the phases that comes into it, and how from small grain a complete planet is formed. अच्छा, ठीक. Okay. Now. I am studying planetary genesis and planetary evolution, structural evolution. So my study would not start from a protoplanet. My study would start from something called a magma ocean phase. What is the magma ocean phase? ये जो lumps are, they are getting, they are accelerating, घूम रहे हैं, so they would heat up. It would form very high temperature magma, and it would form a complete ball of magma. You assume it's a magma का ball, it's rotating. That's called a magma ocean. Complete liquid. Now yes, because of the atmospheric telescope, we have the Kepler mission around 2011, or because although Kepler found many planets through radial velocity method, and after that, around 2019 or 21, 17 Kepler got decommissioned, and then we had the James Webb. James Webb is very advanced and it's very good for studying the atmospheres of exoplanets. So we have the advantage of studying habitability. Okay. Now the question still remains: does any of these worlds harbor life? Or the more importantly, will we be able to tell? Okay. See, not everyone have this machine, so we cannot just Rakesh man ki tarah button lगा के नहीं बना सकते. So we need to find other ways to look for life. Those ways are called biosignatures. Biosignatures are basically some information or evidence that you get to confirm that there is life. ठीक है? Now, suppose there are two life forms. Okay? Assuming that it is not something which can sustain or energy or something like that. So, how a life form needs energy to survive? Okay? What is the biggest source of energy for any life form?
Star.
The star, the host star. So, you agree? What I am saying is, suppose there are two life forms. एक जो किसी और सोर्स से एनर्जी लेता है, दूसरा जो अपने होस्ट स्टार से एनर्जी लेता है. सो ओवर अ लॉन्ग पीरियड ऑफ टाइम किसके मिलने की प्रोबेबिलिटी ज्यादा है? होस्ट स्टार में, बिकॉज इट हैज एन अबंडेंट सोर्स ऑफ एनर्जी. सो देयर आर मल्टीपल प्लैनेटरी सिस्टम्स, सो वी एज्यूम कि जितने भी मोस्ट प्रोबेबल लाइफ फॉर्म्स जो होंगी, बी माइक्रोस्कोपिक लाइफ फॉर्म्स, दे वुड टेक एनर्जी फ्रॉम देयर होस्ट स्टार. So, in process of taking energy from the host star, oxygen is released. Like you get that na H2O break हो रहा है, photosynthesis, something similar to photosynthesis. Okay, you would need oxygen. Oxygen to be released to extract the energy from the host star. अच्छा, अब क्या? So, does that mean oxygen is a good biosignature? I mean, it is. It's a good biosignature. But is it a confirming one? No. तो अच्छा, यहाँ तक I have covered the basics. प्लैनेट क्या होता है, कैसे बनता है. इसके बाद में प्लैनेट फॉर्मेशन चालू करेंगे. If you want to leave, you can leave. अभी तो अच्छा इस केस तक मैं क्वेश्चन पूछ रहा हूँ. कुछ है?
The biosignatures we are getting, we are finding is because of the secondary eclipse on our side.
कौन सा?
The secondary eclipse, emission spectrum of secondary eclipse. And we are.
No, you take both the spectrums.
Yeah.
Emission or
Both spectrums. So, and we are just comparing with the simulated spectrum in the lab. So, we can calculate the synthesis spectrum into different compositions or different elements.
yes, you can.
So, how do we say with certainty that this is the
So, when I told you to a permutation combination, that is not entirely true. Okay. There are different types of algorithms, there are Bayesian methods to search for the most appropriate element that would fit the spectrum. Okay. The way I told you, it was a very rough way. Yeah. There are different types of models. You make a model for doing the retrieval and you run it. So, suppose there are two models. Okay. Both the models might point towards different thing for a certain planet. It has happened. Okay, currently around 2022, Nicholas planet. There's a planet called K218d. It's a Haitian world. Haitian world क्या होता है? It's a water world with a hydrogen atmosphere. So according to Dr. Nicholas, he's a professor in Cambridge University. According to him, he thinks he has found life there, microscopic life, because he thinks there is a faint signal of DMS, dimethyl sulfide, which is a very good confirming biosignature. But in his department only, there is another professor, and he has a paper on the same planet, and according to his model, it is a magma world. So people have very conflicting opinions. I am of the opinion that Niku ka paper is better. You can study your model, so it depends model to model. If your model has a better accuracy, it is most trustworthy.
but that is the only way we can study the
Yes.
If you go back to the AM slide, there was a luminosity increasing twice.
Transit time.
Though, but here acceleration became a transition.
Yeah, so you are getting two light sources, ना? एक स्टार का, then you are getting इसका accretion spectrum, दोनों का light. जब ये सामने आ गया ना, this is blocked some part of light, तो उसकी वजह से नहीं पाएगा. और जब पीछे गया तो जो planet release करता है वो बंद हो गया. तो this is actually a little wrong in this code. It's not equal sizing, like something like this. पहला वाला dim primary बड़ा होता है. Second वाला is a very small notch. और
So when you talk about life forms in other planets, can it always be carbon based or any other element based?
Yeah, so the point is any other element means I talked about taking energy from the host stars. It is an assumption, it might be wrong, that it has to be silicon based or carbon based to take energy from the host star.
So from this method, all we are getting to know is the atmosphere of the planet
Atmosphere and radius.
and radius.
Atmosphere is after doing a lot of data processing.
Yeah.
जो primary information you will get would be the radius because it's like a shadow जो आता है.
So like, don't we get any insight into the surface of the planet? Right?
No, so for that we have to make models. उस पे मैं आता हूँ. That is in the next one. Any other questions? Move on करें आगे.
Yes.
ठीक है. बस ऐसे हो गया. All positive. Okay. Now the question comes is, देखो, whenever you study planet formation, there are two things. Something called a secondary atmosphere and a primary atmosphere. जब भी accretion हो रहा है तो जिसमें जो gases है, few gases which are very prominent in the universe are hydrogen and helium. Every planet while formation has a hydrogen helium का atmosphere. It's called its primary atmosphere. But if the mass of the planet is very small, it would lose its hydrogen helium बहुत heavy gas है. So if the mass is not very good, वो lose it, वो चला जाएगा. For example, even Earth mass, most of the terrestrial planets lose their primary atmosphere. Then the atmosphere we have currently is our secondary atmosphere. Now what is the secondary atmosphere? होता क्या है? अब ये magma wall है. फोटो है क्या? Yes, okay. This is a थोड़ा सा late stage जब solidification चालू हो गया. Imagine जो पूरा जो red वाला system दिख रहा है, this is completely a magma compound. This magma wall will evolve. It would have some elements, some reaction would take place, some gases would outgas. Like not like a volcanic eruption, it's like surface पे से gases release होंगे. Now these gases would form another envelope. This is your secondary atmosphere. In cases of bigger planets, suppose terrestrial planets that are big enough, what happens if they have their primary atmosphere? The secondary atmosphere that is released, it would react with the hydrogen and helium and it will form more composition and you have to do more study of that. अच्छा, अब क्या होता है कि magma ocean जो है, it would have good convection. Convection समझ रहे हैं ना? Good convection. अब convection से क्या होगा? The heavier elements would sink inside, right? So अभी iron जो होगा, वो अंदर जाएगा, and it would form a core. It could be a solid core. Might be a liquid core, but अभी हम rocky planets की बात करेंगे, ठीक है? अब हम planetary से planet की बात कर रहे हैं, habitability की. So mostly habitability में we are talking about rocky planets. Okay. And the planets we are studying are not around sun-like stars. They are super Earths around smaller stars. Achha, can anyone tell me why I am studying bigger planets around smaller stars?
Because you talk about more of the light.
They are more precise when I do the observation of transit. If the star is very big और उसका planet सामने बहुत छोटा सा है, ठीक कितना सा है? My error value will increase. There are chances that I might not get enough data. So my mostly studies are based on small star G type, brown dwarfs के around हम study करते हैं. Okay. Now, and we are studying rocky planets. क्योंकि life form के लिए rocks. You need a rocky planet. Gas giants okay. Now अब क्या होगा? तो magma का ball था. The iron will seep in and it will form a core. Solid core. Suppose we are taking a solid core. So this ball of iron you see, this is a solid core that will be formed. Now imagine it has a solid core and magma around. Okay. Now what I'm going to show, okay, good. अब क्या होगा? There are some
time scale क्या है solidification का?
अरे बहुत डिपेंड करता है और कुछ उसमें.
क्या मतलब कुछ?
मैं तो 10 to 9 years देखते हैं, कभी एडमिशन देखते हैं.
तो जितना बड़ा रेडियस होगा solidification का टाइम लगेगा.
हाँ, it depends planet to planet and even the composition जो उसके अंदर gases हैं. और तो उसमें डिपेंड करता है. तो अब हम देखेंगे कि कैसे solidification हो रहा है. अगर एक इक्वेशन समझ नहीं आई, मत समझो मेरी बात. जो planet है, स्टीफन बोल्ट्जमैन लॉ लगाएंगे हम कि planet ठंडा होगा, ओके? वो हीट आगे निकाल रहा है, आउटवर्ड्स कर रहा है, and there is some temperature Tp हमने ले लिया. What is Tp? Tp is basically a abstract concept temperature. It's the temperature of the mantle. Okay, adiabatically take it to the surface. If you don't get it, forget it. ठीक है, it's fine. So अब क्या है, planet ठंडा होगा. कैसे ठंडा होगा? Would radiate heat, right? So this is a thermal equilibrium equation. This is just an equilibrium equation. अब एक side है, if you see the right hand side, this is the कि flux कैसे ठंडा हो रहा है. Now अब planet गर्म नहीं होता है अंदर से. What are the ways the planet is getting heated? Any ideas? Star. जो star है planet का, it is जो host star है that is heating up the planet, or
radioactivity.
yes, radioactive processes inside are heating up the planet. Under suppose it's an Earth-like planet. So Earth-like planet peaks say something. It's a bulk silicate Earth. Our Earth is a bulk silicate planet. तो जो bulk silicate है उसमें जो silicates होंगे वो आपस में change होंगे. The fusion of silicates will produce something. उसके अलावा हाँ क्या?
between the molecules and
That is very negligible compared to the temperature we are talking about. बहुत ज़्यादा temperature है. Other thing is tidal heating. अच्छा, what is tidal heating? पूरा magma ocean है, so it's fluid. Okay, there is a rocking. So जैसे Earth में, suppose this is a planet, Earth है, जो ocean है, it will form some tidal bulge ना, because of the gravitation of the moon. ऐसे ही the planet, the magma ocean, would form a tidal bulge because of the host star. ठीक? Now, the planet is rotating. This bulge would have an initial mass, तो ये bulge हल्का सा shift होगा. You get an idea? वो नहीं करूँगा मैं. You get an idea? कि ये star है.
बड़ा बड़ा बना दो.
ये तुम्हारा star है. ये तुम्हारा magma ocean है. ठीक है? Suppose this is your core. जो tidal bulge बनेगा. पहले मान लो तुम्हारा tidal bulge कुछ ऐसा था. Right? Because of the rotation, it would be a little ऐसा. You get? मतलब समझ में आ रहा है? ऐसे bulge बनाओ because वो घूम रहा है तो उनका सब rotation है ऐसे. This is understandable, but doubt नहीं है. I can move forward. Okay. This is called a constant phase line. और इसकी वजह से there is some heating going on. उस पर हम नहीं जाएंगे. There is also lots of mathematics that I put around potential. So you get how the planet is heating up and cooling at the same time. तो अब हम magma ocean को solidify करेंगे कैसे? Eventually the planet would cool down the solidification. अच्छा अब solidification कहाँ से होगी? अगर question comes. हम assume कर रहे हैं कि solidification होगा from the radius, core radius RS, जहाँ से core हमारा खत्म होता है, from bottom to top. Okay. But अगर bottom to top solidification हो रहा है, अगर bottom to top solidification हो रहा है, तो अर्थ का जो mantle है वो liquid कैसे है? Valid question, right? So अर्थ में क्या हुआ है? There has been ocean formation. There are multiple factors. इसमें क्या होता है? Something called a crust formation. मतलब वो नीचे से solidify हो रहा था, but ऊपर का temperature जल्दी drop कर गया. So it has formed a lid. समझ रहे? Like an eggshell. ऊपर एक shell बन गया. Now lid can be formed multiple types. Two of them are called stagnant lid and a mobile lid. Stagnant lid मतलब एक complete अंडे का shell. Mars is a stagnant lid. ठीक? एक complete shell बन गया. Somehow temperature drop, इतना बड़ा crust बन गया. अब mantle बन गया. अर्थ में क्या हुआ? वो जो crust की cooling अगर बहुत जल्दी हो जाए, very fast. What happens? You get a mobile lid. मतलब अगर मिट्टी तुमने कीचड़ बनाया, बिना कीचड़ फेंक दो और एकदम से सुखा दो उसमें cracks आ जाते हैं ना? तो उसमें cracks आ जाएंगे. That is called a mobile lid. Now this mobile lid would eventually turn into your plate tectonics. Okay. तो हम आगे चलते हैं. अब mantle जो है तुम्हारा छोड़ दो इसको. Solidify हो रहा है. नीचे से ऊपर. जब mantle solidify होता है, तो there is something called, I'm going to introduce a term called earth oceans. EO. Okay. One earth ocean is a quantity. It means the volume of water contained in the entire earth. It's one earth ocean. Okay. देखो mantle has water inside the magma. Every every planet has some H2O inside its planet. Even have other volatiles, but हमें बस H2O, lots of. तो अर्थ में भी कितना पानी है टोटल? 1 अर्थ ओशन होगा, राइट? सरफेस पे तो मेंटल के अंदर बहुत ज़्यादा, हमको नहीं पता. Okay. So to do this Radix equation, there is something called rho m. This is the density of the mantle. Any idea how do we get the density of the mantle of a planet? Protoplanets. हम तो गए नहीं वहाँ पे. ये तो कुछ नई क्वांटिटी है.
We know the mass and the radius.
नहीं, mantle की density ऐसे नहीं है. It would change. Pressure पे change करेगा. See, it's very high pressure. तो जो अंदर होगा, compress होगा, density change जाएगी. There is something called upper mantle, lower mantle में distinction होता है. हम क्या करते हैं? हम assume करते हैं कि planet में static habitability और अर्थ में. तो जो composition है वो वर्ग सिलिकेट ही है. तो जो अर्थ की डेंसिटी है उसको हम रफली इक्वल मान लेते हैं फॉर आवर कैलकुलेशंस. ठीक है. अच्छा, अर्थ के मेटल की डेंसिटी कैसे करते हैं? This comes under earth science. So what they do is something called seismological study. ऐसा एक मशीन होता है, वो ऐसा seismic wave भेजता है, नीचे से जाती है, रिफ्लेक्ट होकर वापस आती है. Okay, you get it now? Basically, ठीक. Now magma ocean solidification हुआ. अब क्या हो रहा है? The magma ocean is solidified from nature. I am assuming crustal formation अभी नहीं हुआ. Okay? मैं assume कर रहा हूँ कि मेरा planet कोर के surface से टॉप तक solidify हो रहा है धीरे-धीरे. वो ऐसे होके पूरा solid ball में है. Okay? अब जब ये धीरे-धीरे solidify होगा, तो जो उसमें पानी है, H2, the earth oceans inside, उसका क्या होगा? The rocks has a property, solid rocks होते हैं ना, they cannot hold very much of water. Right? टूट जाते हैं ऐसे. So the water would seep up into the molten magma. इससे mantle की viscosity में क्या फर्क पड़ेगा? पहले जो viscosity थी उसमें और पानी चल गया तो क्या होगा? It would decrease, but it would decrease up to some extent because mantle also has its holding capacity. तो वो और ऊपर मूव करेगा. At the end, eventually it would steam up. और गैसिंग हो जाएगी. Okay, and to start forming the steam atmosphere. ठीक है. जैसे जैसे mantle solidify होगा, पानी बाहर निकलेगा steam atmosphere. अच्छा, तो मैं सोच रहा हूँ अभी मैं सिर्फ steam atmosphere लगा. उसमें और भी mantle में volatiles होंगे, they would react, they would form volatile gases, और ऐसी gases का outgassing होता है, and that's how your atmosphere is formed. अच्छा, ये जो steam atmosphere बना, जो sun से radiation आ रहा है, solar SUV radiation, that would break your steam atmosphere H2O into hydrogen and oxygen. Now, because my planet was not big enough to sustain my primary atmosphere, hydrogen भाग जाएगा, escape कर जाएगा. And while escaping, it would take some of the oxygen. So you will get an eventual oxygen का atmosphere. This is your magma ocean solidification. यहाँ तक clear है? मैं कोई ज़्यादा maths में जा रहा हूँ, थोड़ा सा pop science कर रहा हूँ, that's fine. हाँ.
You talk about magma ocean solidification, but what is the main source of solidification? Like how does it solidify? Temperature change, but what is it? Like it just changes the temperature with time, like the energy loss.
अरे so the evolution 10 to the power 9 years तक देख रहे हैं. बहुत साल धीरे-धीरे ठंडा हो जल रहा है. Okay. Now the volatile. अच्छा, volatile मॉडल क्या होता है? Suppose हम एक स्टेज पे हैं जहाँ पे थोड़ा सा मैग्मा ओशन सॉलिडिफाई हो चुका है, कोर है और मैग्मा और गैसिंग हो चुकी है, हल्का सा स्टीम एटमॉस्फेयर बन चुका है, ऑक्सीजन है. ओके, इस स्टेज पे थोड़ा सा you have your solid core, you have your solidified magma, थोड़ा सा मैग्मा ओशन है, and you have your steam atmosphere. ये steam atmosphere धीरे-धीरे एक ऑक्सीजन के एनवेलप में कन्वर्ट होगा बिकॉज़ ऑफ द रेडिएशंस, राइट? सब एग्री कर रहे हैं? अच्छा, क्या होगा ना, जो मेटल, इसमें कई सारे मेटल्स, दिस इज मैग्मा इज योर वोल्टेज मेटल्स होंगे, इसमें कई सारे ऐसे स्पीशीज होंगे व्हिच वुड गो अप, दे वुड ऑक्सीडाइज एंड देन गो बैक इन. समझ रहे हो? फॉर एग्जांपल Fe2O ऊपर आता है, सरफेस पे होता है, इट ट्रैप्स द ऑक्सीजन फ्रॉम द एटमॉस्फेयर, ट्रांसफॉर्म टू Fe2O3. Fe2O is heavier and then sleeps. फिर नया Fe2O का FeO का मॉलिक्यूल ऊपर आएगा, सीप करने अंदर जाएगा. तो अब हो क्या रहा है? जो एटमॉस्फेयर में ऑक्सीजन है, that is getting back trapped in. Right. This is called an oxygen sink. ठीक. Now the question comes कि किसी planet पे अगर ऑक्सीजन है, this completes your planet formation model for rocky planets currently. ये मॉडल जो है दिस इज ओनली वैलिड टिल 5 अर्थ masses. Any वो speculations why?
Because it will not lose its primary atmosphere if it is
नहीं तो फिर प्राइमरी एटमॉस्फेयर में लगा दो ना.
If the mass is
See, primary atmosphere में only thing that I have to add is जो ऑक्सीजन बन रहा है, I would add e hydrogen helium भी है and their reaction equation. See, these are the equation. जो reaction हो रहा है, I would just add hydrogen helium. So what happens is when you go way above 5 Earth mass, you start transitioning from super Earth to main atmosphere to sub Earth. अब क्या होता है? The physics changes drastically. ये पूरा हाइड्रोस्टैटिक इक्विलिब्रियम जो मैं लगा रहा हूँ, टेम्परेचर चेंज, दिस इज नॉट वैलिड. कुछ नहीं पता. सब नेपट्यून के अंदर क्या चल रहा है, गैस जाइंट्स के अंदर क्या चल रहा है, कोई आइडिया नहीं. वेरी थिक एटमॉस्फेयर इंटीरियर प्रूव करना इज नेक्स्ट टू इम्पॉसिबल. इनडायरेक्टली प्रूव करने का तरीका है, बट पीपल आर स्टिल वर्किंग ऑन इट. अगले 5-10 साल तक कोई आइडिया नहीं. ओके, तो अब क्या हो रहा है? You understand ऑक्सीजन सिंक ना? अगर मैं बोलूं किसी प्लैनेट में मेरे को ऑक्सीजन मिला, now if is it due to a life form? ये किस पे डिपेंड करेगा? विशु, अगर मुझे किसी प्लैनेट पे ऑक्सीजन मिला, to say that कि this oxygen is produced due to life form, ये किस पे डिपेंड करेगा? हाँ.
सिंक लाइक सिंक की जो एफिशिएंसी होगी, अगर
Yes.
सिंक की एफिशिएंसी से पूरा ऑक्सीजन डिप्लीट हो गया प्राइमरी वाला,
It would depend on the functionality of the oxygen sink. क्योंकि जितने भी रॉकेट प्लैनेट्स बनेंगे, they would have some more portions of water in them. आउटगैसिंग होगी, स्टीम एटमॉस्फेयर बनेगा. ठीक है, ऑक्सीजन बनेगा, हाइड्रोजन एस्केप करेगा. ऑक्सीजन एनवेलप तो बनना ही बनना है. Now to say that जो ऑक्सीजन किसी प्लैनेट में मुझे मिला है, वो किसी लाइफ सोर्स की वजह से ही है, नॉट बिकॉज ऑफ जियोलॉजिकल प्रोसेसेस. इट हैज टू बी कि जो है वो सिंक है. अगर इफ इट्स फंक्शनिंग वेरी वेल, इट वुड टेक ऑल योर ऑक्सीजन. ऑक्सीजन को वापस अंदर ट्रैप कर लेगा. ओके, सो अब मैं क्या करूंगा, मैं जो बैकमैन मॉडल है उससे मैं 3 सिनेरियो स्टडी करूंगा. ठीक है, जैसे 5 to 10 अर्थ ओशंस, 10 to 250 अर्थ ओशंस और लेस देन 0.3 अर्थ. इन तीनों सिनेरियो में आई एम अज्यूमिंग दैट द प्लैनेट बाद में हैबिटेबल नहीं है. ठीक है, मैंने मान लिया कि द प्लैनेट आई एम स्टडीइंग इन माय सिमुलेशंस इज नॉट हैबिटेबल, बट इन दीस सिनेरियोस आई वुड शो कि इसमें अनहैबिटेबल प्लैनेट में एबियोटिक ऑक्सीजन समझ लो ना, जो बायोटिक ऑक्सीजन आ रहा है, एबियोटिक ऑक्सीजन एक्टिवेशन होता है, 6 मैलफंक्शन होते हैं. ओके, दैट इज व्हाट वी आर गोइंग टू स्टडी. अच्छा, चलते हैं. पहला है हाई CO2H2 इनिशियल ह्यूमिडिटी. इसका मतलब है कि CO2 जैसे कि हेवी गैस, अगर स्टीम एटमॉस्फेयर के साथ और भी गैसेस रिलीज होगी, यू गेट दैट आइडिया ना. अभी बस स्टीम की बात करें, मतलब मल्टीपल गैसेस रिलीज एटमॉस्फेयर में, वो होगी, उनका कुछ प्रेशर होगा. हमारे एटमॉस्फेयर का प्रेशर हर बार के अराउंड है. इन सब प्लैनेट्स यू वुड सी 100 बार तक का प्रेशर जा रहा है. सो वहां क्या होता है, व्हेन द प्रेशर इज टू मच, when the pressure is too much, what happens is because of this pressure जो matter है ना उसकी solubility बढ़ जाती है. So the reducing species जो ऊपर आके तुम्हारे सिंक की तरह काम कर रही थी, they will stay dissolved inside, वो ऊपर नीचे नहीं जाएगी. So your sink will stop, right? And eventually the planet will solidify. तो इससे क्या होगा, एक ऑक्सीजन एटमॉस्फेयर बन जाएगा इवन अनहैबिटेबल. अच्छा, now if you want to see कि उसमें ऑक्सीजन रहेगा, ये सब में हटा दो. yes. Now the second option is water world. Water world हम मानते हैं around 50 to 250 Earth oceans. अच्छा, Earth did not turn into a water world, complete water world, क्योंकि थोड़े से Earth oceans कम थे, but ocean formation. So life also depends sometimes on ocean formation. ocean formation क्या होता है? अब जब steam atmosphere बन रहा है, so you get ना कि जो ऑक्सीजन बन रहा है स्टीम से, वो सारा एक साथ तो बनेगा नहीं, right? Because of the solar external radiation, the oxygen that is being formed in the steam envelope, that is not spontaneous. वो धीरे-धीरे बन रहा है. It's a very long, slow process. तो at some time there will be lots of steam in the atmosphere, lots of oxygen. तो एक पॉइंट के बाद ह्यूमिडिटी बढ़ेगी, ह्यूमिडिटी I don't know if it's the right term होगा, एक पॉइंट के बाद दिस टीम would condense and form oceans. You get that? Ocean formation हो जाएगा. 250 और oceans में हम बात कर रहे हैं. तो ocean formation जब होगा तो पानी आएगा. अब जब ocean formation होगा तो जो surface का temperature है that would change very fast. Right? Planet बहुत जल्दी solidify होगा. तो वहाँ तुमको कुछ और जैसा केस मिलेगा. Where you would have a rock solid core. ठीक है, थोड़ा सा मैग्मा हमारा सॉलिड हो गया, थोड़ा सा मैग्मा एंड यू हैव अ सॉलिड क्रस्ट. यू गेट ना? सॉलिड मेटल यू हैव सॉलिड क्रस्ट. अब जब ये क्रस्ट फॉर्मेशन हो गया तो सिंक्स बंद हो गया, राइट? स्पीशीज का नाम वो कैसे तरह ऑक्सीजन इनसाइड. सो क्रस्टल फॉर्मेशन इज वन रीजन जहां पे वाटर वर्ल्ड्स वुड स्टॉप द सिंक एंड जो हमारे एटमॉस्फेयर में एनवायरमेंट ऑक्सीजन मिलेगा. तो वाटर वर्ल्ड है, उसमें ऑक्सीजन मिल रहा है, बट मैंने क्या दिया हैबिटेबल है. तो वाटर वर्ल्ड विद ऑक्सीजन इज आल्सो नॉट कंफर्म्ड हैबिटेबल. ठीक, इसके बाद आता है डेजर्ट वर्ल्ड्स. डेजर्ट वर्ल्ड यू कैन इमेजिन समथिंग लाइक दिस ऑन डी. नाउ द प्रॉब्लम विद डेजर्ट वर्ल्ड इज, कोई आईडिया क्या होगा डेजर्ट वर्ल्ड में? So when you talk about desert world, it's usually less than 0.3 earth oceans. जब इतना कम पानी है earth oceans, तो डेंसिटी जो क्या कहते हैं तुम्हारी विस्कोसिटी होगी मेंटेन की, that would be originally very high. Because such a high viscosity, solidification थोड़ा तेज होगा. You get what I'm trying to say? So desert world में solidification बहुत steep होता है. You can see this. So that's solid world. You can now, yeah, I will put this, you can see slides के level things. Fine. So desert world में एकदम से solidification बहुत fast होगा. जो atmosphere बना, steam हो सकता है sinks function कर रहे हैं, but the sinks would freeze, solidify very fast. So even in desert worlds, you can have an oxygen accumulation, which is from abiotic sources. Okay? So मैंने तीनों scenarios किया, बताया तुमको, जहाँ पे different level of ocean composition है, you can get uninhabitable planets. तो इससे एक conclusion निकल सकता है कि oxygen alone is not a very good biosignature. सिर्फ oxygen मिला तो मैं नहीं कह सकता, क्योंकि अच्छा, some people say कि methane is a good source, लेकिन सिर्फ methane and oxygen is also not क्योंकि मार्स पे methane है, मार्स पे oxygen भी था, मार्स पे लाइफ है. क्या ही
हो सकती है.
you cannot say, but correctly नहीं है. So even oxygen and methane are not. DMS का we can say for some certainty, if you get time high sulfate, that is produced from it. So this was the planet formation model. बाकी मैं मॉडल के बारे में बहुत चीजें, तो मैंने कई चीजें तुमको roughly बताई हैं, आपको बताई हैं कि you do like a permutation formula, it's not permutation formulation. Okay, you do a Bayesian analysis to find the best ranges where an atmosphere can be fitted. You make something called a pressure temperature curve. जो तो बस atmosphere मिलता है. You start by making a pressure temperature profile. PD profile आ गया. उसके बाद you make something called a 3D GCM. GCM मतलब general circulation models. GCM क्या है? तीन तुम्हारे dimensions हैं, which is the latitude, the longitude and the altitude. हर गैस का composition, latitude, longitude और altitude पे कैसे change कर रहा है? You make these curves in the atmosphere and then you study. Okay, thank you everyone. That was. The only problem in this, if you encounter life forms like energy and heat loss, they can say, हाँ.
डेजर्ट वर्ल्ड वाले जो सिलिकेट है क्या वो सिलिकेट से तो ऊपर की तरफ जा रहा है.
वो सिलिकेट फ्रीज कर जाते हैं मेटल में, सॉलिड सिलिकेट में जो कन्वेक्शन चल रहा है ना, सो जब हम बॉन्डिंग करते हैं, वी अज्यूम दैट कन्वेक्शन इज गुड इनफ, और कन्वेक्शन के थ्रू हीट स्प्लिटिंग. देयर आर टू वेज टू मॉडल अ प्लैनेट. ओके, द वे आई यूज स्टेफन बोल्ट्जमैन इक्वेशन. तो मैं बस टेंपरेचर का चेंज देख रहा हूँ. आई एम अज्यूमिंग कि बिकॉज ऑफ द कन्वेक्शन देयर इज एन इवन डेंसिटी अप टू सम पॉइंट. मेटल में डेंसिटी सेम रहेगी ना, कन्वेक्शन हो रहा है, यू चेंज लेयर बाय लेयर. सो मैं अज्यूम करता हूं कि बिकॉज़ ऑफ कन्वेक्शन थोड़े टाइम के लिए इवन डेंसिटी, देयर इज अ 5 gigapascal के अराउंड डेंसिटी बहुत ड्रास्टिकली चेंज होती है, ठीक है, if you assume a common density, okay, so that's what happens. तो मैं दो तरीके, या तो मैं स्टेफन बोल्ट्जमैन इक्वेशन यूज करूँ जिसमें मेरे को देखना ही नहीं कि प्लैनेट के अंदर कैसा प्रोसेस चल रहा है, मैं बस देख रहा हूँ कि टेम्परेचर को चेंज कैसे हो रहा है, और बिकॉज ऑफ द कन्वेक्शन मैंने अज्यूम कर लिया कि अप टू सम पॉइंट आई हैव अ सिंगल डेंसिटी, तो मैं आराम से मॉडल कर पाऊंगा। सेकंड में होता है आई यूज रेनॉल्ड्स नंबर, इसमें मैं डेंसिटी चेंज देखना है, फिर पूरा कंडीशन होगा, सो उसमें तो सीधी कैलकुलेट हां
तो वाटर वर्ल्ड में जो फंक्शन होता है वो
क्योंकि क्रस्ट फॉर्मेशन हो गया ना, ऑक्सीजन सिंक क्या है, हमारे लेयर में मैग्मा है, उसमें से गैस निकलती है, उसमें क्या होता है कि तुम्हारा कोई और ऊपर आता है, ऑक्सीजन होता है अंदर से, अब एकदम से वो फ्रीज कर दिया तो कुछ होता क्या है, मतलब जैसे लीक गेट इट, बंद हो गया क्रस्ट फॉर्मेशन में। सो किसी भी प्लैनेट में जहां क्रस्ट फॉर्मेशन हो गए तो 6 क्रस्ट फॉर्मेशन में बंद हो गए, 6 हो सकता है वर्क कर सकता है लॉन्ग स्टेट में, पता है हो सकता है तुम्हारे 6 सारा एटमॉस्फेयर ऑक्सीजन ले ले और तभी 6 ना हो, तभी तुम्हारा क्रस्ट फॉर्मेशन।
Harshit, questions come.
कौन गेट बंद किया? अच्छा, if you are interested in the field and want to read a little bit, there is a book called the Exoplanet Handbook by Michael Benjamin. That is a good read. It has all the basics. जितना भी तुमको चाहिए। अच्छा, आगे इस फील्ड में क्वेश्चंस क्या-क्या हो रहे हैं? जैसे कि मेंटल में there is something called olivine, जिसमें अर्थ साइज के सबसे होता है। बट क्वेश्चन ये है कि olivine हमेशा olivine था क्या? हमारे जो सेस्मोलॉजिकल स्टडीज है मैक्स 50 साल 100 साल पहले की होगी, इनकी बात 100 150 400 साल पहले, उसके पहले मिलियन ईयर पहले सेम कंपाउंड था, इसकी क्या गारंटी, कोई गारंटी नहीं, राइट? मिनरल्स आपस में इंटीरियर जियोकेमिस्ट्री रिएक्ट किया, उस पे volatiles बने, these volatiles went down to the atmosphere, okay, that's how the planet formed, different atmosphere. So my project that I'm working on, the first part was structure and evolution. हमने स्ट्रक्चर बनाया कि कोई प्लैनेट का ये रेडियस है, ये मास है, तो उसका कोर कितना बड़ा होगा, कोर का मास क्या होगा, मैग्नेटिक कितना बढ़ेगा, स्ट्रक्चर एवोल्यूशन, वो सॉलिडिफाई कैसे होगा, कितना टाइम लगेगा, एटमॉस्फेयर कैसे बनेगा, कितना टाइम लगेगा। नेक्स्ट पार्ट दैट आई एम ट्राइंग टू डू इज अबाउट द इंटीरियर केमिस्ट्री, इसमें वी आर ट्राइंग टू फाइंड आउट कि जो अंदर द मैंटल में जो केमिकल्स हैं वो आपस में कैसे रिएक्ट कर रहे हैं फ्रॉम डिफरेंट लेयर्स में, कैसे वर्नाइज बन रहे हैं और कैसे कैसे हो रही है, किस में। सो द एंड गोल ऑफ माय प्रोजेक्ट इज इट्स कॉल्ड सरफेट सरफेस एंड स्ट्रक्चर एंड एवोल्यूशन ऑफ एक्सोप्लैनेटरी इंटीरियर्स। सो इसका गोल ये है कि अगर मुझे कोई प्लैनेट का एटमॉस्फेयर मिला ना, मैं ये बता सकता हूँ कि उसके इंटीरियर में क्या क्या है, क्योंकि द एटमॉस्फेयर इज रिलेटेड विद द इंटीरियर, जैसे इंटीरियर होगा, इंटीरियर रिएक्ट करेंगे, वोल्टाइल्स बनेंगे, वोल्टाइल आउट गैस होंगे, अगर प्राइमरी एटमॉस्फेयर उससे रिएक्ट करेगा, नया एटमॉस्फेयर बनेगा। सो फ्रॉम द करंट एटमॉस्फेयर आई कैन टेल कि इसका इंटीरियर क्या था, बिकॉज इंटीरियर इज काइंड ऑफ वेरी नेसेसरी इन अंडरस्टैंडिंग हैबिट। ओके, थैंक यू।
What are the techniques that you use to identify the primary elements that are functional? Like which one
Elements are
you told na like बाद में they get like they change and now
So,
we
what
are
are
seeing
you
change. So what are the
There
techniques?
has been no work done on it because to study high temperature pressure, this you need special laboratories that are not big. To solve it, the amount of pressure and temperature, your normal chemistry does not work.
So how do you study evolution then? Like पता कैसे?
So basically, there are multiple techniques. We try to find some thermodynamic, and so these chemicals evolve, and they have a phase shift that they are studying. अभी तो मैं कर लूँगा तो ऐसे बता दूँगा. But currently, I don't think I have a very good grasp of it. Like how I'm going to do that. 2 साल बाद 2 साल बाद.